The theory of plate tectonics unified the Earth sciences as never before. All sorts of geological phenomena, great mountain ranges and wide oceans, fertile plains, valuable ore deposits, the most destructive natural disasters like earthquakes and volcanoes, they can all be understood in the context of moving plates on the Earth's surface. In this lecture, I examine the underlying causes of Earth's geological features and its violent crustal events. We'll see that most earthquakes and volcanoes arise from dynamic processes associated with plate motions. I'm going to review the evidence for plate tectonics, and then I'm going to examine the nature of Earth's tectonic plates and their three types of dynamic boundaries. These three types are divergent boundaries, like the Mid-Atlantic Ridge, where new crust forms along a chain of volcanoes, and then convergent boundaries, like the coast of the Pacific Northwest, where old crust is swallowed up, and finally transform boundaries, like the San Andreas Fault, where two plates scrape by each other. And we're going to see that these boundaries control the locations of most of Earth's earthquakes and volcanoes. In the last lecture, I showed how the theory of plate tectonics brought together observations from many different disciplines of the earth sciences. We saw 6 lines of evidence that together make a compelling case for the theory. First, we had the shape of the continents. That was the S-shaped eastern coasts of North and South America, which appear to match almost perfectly the western coasts of Europe and Africa. The match is especially good if you look at the continents all the way to the edge of the continental shelves. Such a jigsaw-like match seems much more than a coincidence. And then the second line of evidence, that was the matching rocks and fossils across the Atlantic Ocean. The same unusual fossil species are found in New England and matching localities in Wales. And distinctive rock formations line up in the southernmost parts of South Africa and South America, and the great diamond deposits also, the ones of Africa's west coast, lie directly across the Atlantic from the diamond fields of Brazil. And then earthquakes and volcanoes also provided evidence for the plate tectonics. These features occur predominantly in bands and in chains, most notably that ring of fire around the Pacific Ocean. All this intense activity points to something unusual happening along those narrow zones. And then there was the dramatic discovery of ocean floor topography. That was in the 1950s. The dramatic mountain ranges form tens of thousands of miles of mid-ocean ridges. And most notable is the Mid-Atlantic Ridge, which neatly bisects the Atlantic. And of special significance was the shape of the Mid-Atlantic Ridge. That shape exactly parallels the continental coastlines on both sides of the Atlantic. And then there was a 5th line of evidence. That was provided by the ages of volcanic islands in the Atlantic Ocean. Iceland, that's a volcanic island right on the ridge, is still volcanically active, and islands close to the Mid-Atlantic Ridge are quite recent, but the farther away from the ridge you go, the older are the volcanic rocks that form the islands. And finally, that smoking gun of plate tectonics, the piece of evidence that convinced all but the most die-hard skeptics, was the pattern of rock magnetism on the ocean floor. Scientists found those long stripes of magnetic rock parallel to and symmetrical about the mid-ocean ridges. The volcanic rocks freeze into signature of Earth's magnetic field. So immediately adjacent to the ridge, the magnetic field matched that of today's Earth, but farther away, the north and south poles were reversed. Of course, this discovery was significant because it revealed that the magnetic field does this amazing flip-flop. But the field reversals also revealed the nature of plate motions. A succession of bands, alternately normal and reversed, appeared parallel to the ridges and symmetrical about the ridge. The only logical explanation was that the mid-ocean ridge was a place where new crust was being formed. This observation was clear evidence that the ocean floors were spreading apart. In science, simple theories that explain a whole wide variety of observations in a single unifying framework, those are the ones that are most prized, most valued. Plate tectonics is just such a grand theory. It ties together data on minerals and on fossils, on earthquakes, volcanoes, on surface geology, and also the structure of the planet's deep interior, and much, much more. Plate tectonics is crucial to understanding long-term variations in climates, to documenting the distribution of ore deposits, to deducing pathways of life's evolution. In this lecture, it's the 39th of the series. I'm going to examine plate tectonics and its consequences in more detail. But first, let's take a closer look at the distribution and the physical characteristics of the plates themselves. In an earlier lecture, the Earth's interior was described in terms of 3 chemically distinct layers. Remember, there was the core. That's the central layer of the Earth. The core is made of a dense ball primarily of nickel iron metal. There are extreme conditions down there, several thousands of degrees, more than 1 million atmospheres pressure. The core is further divided into a solid inner core and then a liquid outer core. Okay, then comes the mantle. That accounts for most of the Earth's volume. The mantle is made of dense silicate minerals, is composed primarily of oxygen, silicon, magnesium, and iron. And then finally, the crust. That consists of less dense minerals and forms only the very thin outer shell of the Earth, no more than a few tens of kilometers thick. The crust is made primarily of lighter elements like silicon and oxygen, plus various incompatible elements that sort of formed a frothy, light material of relatively low density minerals. These minerals floated to the surface to form the crust. That's the chemical layering of our planet. But it turns out we can also describe rock layers near the surface in terms of their rigidity, in terms of their strength. And here I need two new words. Those are lithosphere and asthenosphere. Look at this cartoon. The lithosphere, that includes the crust, and the top part of the mantle is relatively thin. It's about 50 to 100 kilometers thick. It's a relatively cooler layer, less than 1,000 degrees centigrade, and it's brittle. So if you had a hammer, it would break the rock. In a sense, the properties of the lithosphere are something like those of a pane of glass. It's thin, it's brittle. The lithosphere rides on top of the relatively soft and hot asthenosphere, which extends deep into the mantle. Deep in the Earth, the temperature is hot enough for the rocks to be relatively soft and plastic. Think of a piece of taffy. You know, it's brittle when it's cold, but softens and it can be pulled when it's warm. See, tectonic plates are simply wide pieces of lithosphere that are shunted about by convective movements of the soft underlying asthenosphere. Take a look at a graphic. Each plate is a relatively thin piece of brittle lithosphere, tens of kilometers thick, hundreds to thousands of kilometers wide. That tectonic plate is supported by the soft, hot asthenosphere below. It's convection of the asthenosphere that moves heat and drives this process. In this scheme, continents, which are shown to the left on this figure, they have to be treated completely separately. They're like giant rafts of relatively light rocks and minerals. They just float on top of the lithosphere. In a sense, the continents are completely an afterthought. They play no significant role whatsoever in plate motions. They just float on top like scum on a pond, and they go along for the ride. Now, a map of the world's tectonic plate shows about a dozen large rigid plates distributed across the globe. Look at this map. Most of us in the United States live on the North American plate, which extends from the Mid-Atlantic Ridge over here to California over here. And then citizens of Hawaii and this very, very small part of the California coast down here, they reside on the Pacific plate. And then the continents of South America here, and Europe, and also Australia, they're contained on single plates. But Asia, notice Asia is split into at least two plates. That's depending on how the boundary between the North American and the Eurasian plates is drawn. And then the African continent is on a single plate, but it appears to be starting to split part along the Great Rift Valley here. It looks as if someday a portion of Eastern Africa may actually split off. Now, these tectonic plates are in constant motion relative to each other. You'll notice that this map of plate boundaries also reveals relative plate motions at divergent and convergent and transform boundaries. You can see the various arrows on the map. Okay, now let's look at three different kinds of plate margins. We have divergent boundaries, convergent boundaries, and transform boundaries. So first, the divergent boundaries. Here's a cross-section. Divergent boundaries mark elongated zones along which new crust is being formed. Two plates will diverge above a region where mantle convection brings heat to the surface. The excess heat causes partial melting of those near-surface rocks, and this magma supplies volcanoes along the spreading axis. So the lava produced at ridge volcanoes is typically basalt. That's a dense black rock. It's rich in oxides of silicon and magnesium and iron. Basalt forms the foundation for all of the ocean crust of Earth. Now, oceans cover about 3/4 of Earth's surface. That's why most of the Earth's surface is covered by volcanic rocks. The surface of the Earth features lots of prominent divergent boundaries. Look at this map. The Mid-Atlantic Ridge, that's the one that extends for tens of thousands of kilometers along the middle of the Atlantic, is now spreading at about 2 to 4 centimeters per year. That's about an inch and a half or so. Satellites can make laser distant measurements, and they can actually detect this increase in distance between points in Europe and North America. The Atlantic has widened by about 2 feet since these measurements began. I want to do a quick back of the envelope calculation to show the consequences of this gradual spreading. An inch or two a year doesn't seem like very much, but let's do the math. Now, the Atlantic Ocean, it's 3,000 miles wide. So let's say at about 1.5 inches per year, how long would it take to open an ocean that wide? Well, they're 5,280 feet in a mile and 12 inches in a foot, so you can multiply that. That's 3,000 miles times 5,280 feet per mile times 12 inches per foot. So it's about 200 million inches. That's how wide the Atlantic is. Now, at about 1.5 inches per year of spreading, you take 200 million inches, you divide it by 1.5 inches per year, and you come up with on the order of 150 million years. That's the age of the Atlantic Ocean at its current spreading rate. But the Earth is more than 4 billion years old. 150 million years is just the blink of a geologic eye. Now, take a look at the map and imagine playing the tape of Earth history backwards. Here's the Earth today. The Atlantic Ocean will get narrower and narrower as you move backward in time. You'd see it close up and close up more. You'd see South America and Africa come together, Europe and North America come together. And then about 150 million years ago, the Americas would merge with Europe and Africa. There was no Atlantic Ocean 150 million years ago. And it turns out, this is amazing, it turns out this is the latest episode of opening and closing in the long history of the Atlantic Ocean and its precursor oceans. Before about 400 million years ago, there was another ocean in its place, and that too opened and closed by plate tectonics. That's amazing to me. The Atlantic Ocean is, in effect, an intermittent ocean. It comes and it goes on a time scale of a few 100 million years. Okay, let's look at that map of divergent boundaries again. One of the most intensively studied divergent boundaries is the Juan de Fuca Ridge. It's here just a few hundred kilometers off the coast of Oregon and Washington State. Now, there are a couple of good reasons why that ridge is so intensively studied. For one thing, there are great oceanography departments along the Pacific Northwest coast at the universities in Oregon and in Washington State. Also, that ridge is just an easy day's voyage from port. That's as opposed to the Mid-Atlantic Ridge, which is much further from land. It takes the better part of a week to travel the 1,500 miles to the Mid-Atlantic Ridge. Well, as a result, the very first seafloor magnetic anomalies were recorded there at the Juan de Fuca Ridge, and today there's a constant network of seismic and chemical monitors to detect earthquakes and volcanic eruptions near the ridge. And oceanographic vessels can arrive quickly. They can study any sort of occurrences. Okay, and here's another important divergent boundary. It's the East Pacific rise in the South Pacific Ocean. That's down here. Now, the highest known spreading rate, as much as 17 centimeters, that's about 7 inches per year, has been measured there. And recent studies have also found that spreading isn't always symmetrical. This is weird. One side can move about twice as fast as the other. And why and how this happens is still something of a mystery. Yet another major divergent boundary is located in the Indian Ocean over here. Now, this is an extensive system, but it's very poorly studied because it's far from any oceanographic center, and it's subject to rather severe weather conditions as well. Well, suffice it to say that most of the Earth's tens of thousands of miles of ridges haven't been studied yet. All of these ocean ridges display complex hydrothermal systems. That's where seawater filters deep underground through cracks, and then it's heated by volcanic activity, and that water comes back up. Here you see a picture of one of those mineral-rich black smokers. Now, these vents support astonishing deep water ecosystems, and they've been found along all the major ridges. What looks like smoke in this picture is actually fine-grained minerals, and they precipitate when hot volcanic water hits the cold ocean. Now, near some of these vents, you'll find the most bizarre creatures, 6-foot-long tube worms. You got giant clams, spider-like crabs, clouds of microbes. These are amazing islands of life, and they're in near total darkness. It turns out that much of the energy comes from the Earth's heat rather than from the sun. You know, these hydrothermal systems suggest a surprising connection between plate tectonics and the distribution of life. There's even a possible connection to the origin of life on Earth, and I'm going to talk a lot more about that in Lecture 54. Now, the Juan de Fuca Ridge, again, it's the most heavily studied of the ridges, but every ridge that's been visited also has abundant life. Now, here's another wrinkle. This is the wrinkle to divergent boundaries. If mantle upwelling occurs beneath a continent, the result may be the eventual breakup of a landmass. Look at the map again. There's an incipient divergent boundary now appearing along the Great Rift Valley of East Africa. You see that feature here. Now, along this rift, you get a deep valley with a chain of volcanoes. That includes Mount Kilimanjaro. That's the most famous volcano in Africa. The Long Valley also features a string of lakes where the continent has thinned. And as the rift extends, the lakes may link up to form one long lake, as shown here. And eventually, such a valley may become a new ocean. You know, there are also places in New Mexico and in Arizona where volcanoes are active, and there's a slight rifting of this kind that seems to be taking place. Now, it's much too early to tell if North America is going to rift. You're going to have to wait another few million years for that story. Okay, now to a second kind of boundary. Convergent boundaries. They mark zones where the relative motion of two plates is towards each other. And this situation rises above zones of downwelling mantle convection. So details of the boundary are going to depend in large measure on whether one or both of the converging plates carries continental material. Think about three distinctive types of boundaries between two converging plates. Okay, you can have an ocean-ocean boundary, you can have an ocean-continent boundary, and then you can have a continent-continent boundary. So if neither plate carries continental material, then one oceanic plate is going to plunge beneath the other one. That's a process called subduction. And similarly, if only one plate carries continental material, then the other oceanic plate invariably subducts beneath the continent, as shown here. More than 95% of all convergent boundaries are of one of these two types, with a subducting oceanic plate. Now, you might think the tectonic plates subduct and are swallowed up because new crust is pushing apart someplace else. However, that's not quite true according to the prevailing view. Cold plates are dense relative to the hot mantle. So think about it. Gravity actually helps pull plates into the mantle. So according to this relatively new point of view, it's a pull due to the force of gravity rather than a push that drives plate tectonics. Okay, rates of subduction are comparable to rates of divergence. That's a few centimeters, an inch or two a year perhaps. That makes a lot of sense, since every time new crust is formed one place, old crust has to be subducted someplace else. You know, there are a lot of distinctive topographical features that go hand in hand with subduction. For example, take a look at this. All the deepest ocean trenches occur when one oceanic plate subducts under and buckles down a second plate. You can see how that might happen right here at that junction. The deepest place in the ocean, that's the Marianas Trench. It's exactly such a place. It could submerge Mount Everest with thousands of feet to spare. Now, many subduction zones are sites of intense geological activity. Remember the geometry of subduction? One plate angles down at perhaps 45 degrees under the other one. And this movement can be jerky, and that motion leads to numerous deep earthquakes that concentrate along that subduction zone. Most of the earthquakes that affect Japan and Alaska, the Middle East, they're of this type. And the deepest of these quakes come from hundreds of kilometers down. They're quite appropriately called deep focus earthquakes. You might recall there's a big Seattle earthquake in March of 2001. That was also a deep earthquake of this type. It was caused when the Juan de Fuca plate suddenly moved under North America. Now, subduction zones are often associated with intense volcanism. This graphic shows what happens when wet crustal material is subducted down into the hot mantle. So the water-rich rocks, they get hot. They move into a deep hot zone where the rocks partially melt. And the resultant magma works its way back up toward the surface. That's here. And the result is this relatively low density magma is much richer in silicon, oxide, and basalt. And so it rises up to the surface and forms these volcanoes. Now, recall from lecture 21 that silicon and oxygen form strong, stiff bonds. For this reason, a silica-rich magma doesn't flow easily, and so it's much more likely to produce explosive volcanoes. The explosion of Mount St. Helens in Washington State was the result of this kind of volcanism. And all of the Cascade Mountains, that's Mount Hood and Mount Adams, and especially Mount Rainier, they have the potential for that kind of explosion. Think for a moment about the geometry of subduction. Because of the slope of the subduction, the resulting volcanoes typically occur 100 to 200 kilometers away from the ocean trench. You have a trench, and then the volcanoes over here. So you often have shallow earthquakes associated with subduction near the coast, and then volcanoes a couple of 100 kilometers inland from there. Now, when subduction leads to a chain of volcanic islands, the result is what's called an island arc. Here you see that kind of situation. Same kind of subduction, same kind of volcanic action produced away from the trench. The Aleutian Islands off Alaska, the volcanoes of Japan, Mount Pinatubo in the Philippines, a lot of the islands in the South Pacific, they're of this type. Subduction also often leads to continental volcanoes. Numerous examples are found along the East Pacific Rim, including the Andean volcanoes of South America, the Cascades of the Pacific Northwest, lots of others. Subduction also contributes to volcanism in Italy, including Mount Vesuvius. This is the famous volcano that killed Pliny the Elder, and it buried Pompeii and Herculaneum. Well, natural disasters aren't the only consequence of subduction. That reworking of the crust by subduction can also lead to the solution and the concentration of valuable ores. See, this happens because water is drawn down into the mantle by subduction, and many metal elements are dissolved by hot water. So this water percolates up through the crust, and when the water cools, the metals may all come out of solution into an ore body of amazing size and concentration. You know, many of the world's richest metal deposits, including gold and silver, their copper, lead, zinc mines, other kinds of mines, are in the American West, and these are associated with ancient volcanoes that form near convergent boundaries. So plate tectonics has provided economic geologists with a whole new strategy for finding valuable ore bodies. They now look for ancient convergent plate boundaries and the associated volcanoes. And then they look around for the associated metal deposits. This approach really works. It's led to the discovery of major new mining opportunities. Okay, there's a third kind of convergent boundary beside the ocean-ocean and ocean-continent boundaries. Occasionally, not very often, but occasionally, two converging plates both carry continental materials. Look at this figure. Because continental rocks are relatively light, they can't be subducted into the mantle. And the results are absolutely spectacular. The tallest mountain ranges in Earth's history have been associated with such converging boundaries. It's pretty obvious why this happens. The two plates keep moving toward each other. But the relatively light continental material just has no place to go. It just keeps folding back on itself into higher and higher mountains. Today, such a collision is happening at the boundary between the Eurasian and the Indian plates. See, the Indian plate is moving north relative to the Eurasian plate, and the two continental masses are crumpled and they're folded into the world's tallest mountain range, the Himalayas. It's amazing that the rocks at the very highest point of Mount Everest are limestones, and those limestones contain fossils of sea creatures. Those are ocean fossils. They're now 35,000 feet above sea level. That's what plate tectonics can do. And this isn't the first time in history. A similar collision of continent-bearing plates took place about 400 to 500 million years ago to form what became the Appalachian Mountains. That's when the previous version of the Atlantic closed up and the Americas crashed into Europe and Africa. That formed a high mountain range. It's now smooth and eroded, but the Appalachians were once as tall as the Himalayas are today. Okay, now to a third kind of boundary. Those are transform boundaries. Now, these are plate boundaries that are simply faults. They're places where two plates grind past each other. It's easy to recognize such a fault because any linear feature is going to be offset by the fault. Now, such boundaries are absolutely inevitable on a sphere if you have both divergent and convergent boundaries. You can't push plates around without having them scrape together someplace. The San Andreas Fault is the longest and the most famous and the most highly active transform boundary today. Major earthquakes occur along this fault every few decades. Geologists predict that another severe quake is likely to strike Southern California in the next quarter century. You know, no one knows how to predict exactly when that quake will happen, but there's no doubt that it will happen. The San Andreas Fault has been moving in big jolts and in jerks for millions of years, and there's nothing we can do to stop it. Okay, there's other transform faults. There are numerous smaller transform boundaries in the ocean. Look at this. All of the Earth's ocean ridge systems, for example, are offset sometimes by several hundred kilometers by dozens of small transform faults. If you look closely at a map of ocean floor topography, you're going to see these features in all the Earth's oceans. Now, this kind of transform fault doesn't mark the boundary between plates. It just relieves the inevitable stress that develops when a long, straight feature like a ridge has to fit on the curved surface of the globe. Geologists have also identified several dormant transform boundaries. That's where two plates meet, but they don't seem to move significantly with respect to each other. There's such a passive boundary that separates the Eurasian and African plates. That's over here. Someday in the future, as crustal stresses build, these boundaries may again become active, and they may become dangerous earthquake zones. What we've seen from this overview is that large-scale mantle convection drives plate tectonics. It controls the location of most of Earth's earthquakes and volcanoes. Divergent boundaries are by default chains of volcanoes, and convergent boundaries also lead to extensive volcanism, albeit about 100 to 200 kilometers under the zone of subduction. Yet, some of the best known and most spectacular volcanic areas, including the Hawaiian Islands and Yellowstone Park, they're smack in the middle of a plate. These volcanoes can't be explained in terms of plate boundaries. It turns out these areas are called hotspots. They're found all over the globe. There are perhaps 100 of them worldwide. You can see from this map that many hotspots are nowhere near plate boundaries. And here we have to invoke a different kind of mantle convection involving narrow plumes of hot, rising magma. That's what produces these volcanic hotspots. The exact process is poorly understood, and that's a really intense area of research these days. Some researchers now suggest that hotspots arise when you have a narrow plume of magma that rises all the way from near the core mantle boundary, almost 3,000 kilometers down. In any case, the location of hotspots seems to be independent of plate tectonic processes. And the Hawaiian Islands, this provides an excellent example of a hotspot in action. Look at this. As the Pacific plate moves over the fixed Hawaiian Islands, that's a hotspot. New islands are going to be formed. The hotspot is now beneath the southern side of the big island, Hawaii. And a new island seems to be forming under the ocean to the southeast. That's just to the northwest off the island of Maui. The great dormant volcano, Haleakala, still has a little bit of volcanic activity left, and it at last erupted in about the 1700s. And then older volcanic islands, including Molokai and Oahu and Kauai, are now extinct. They've moved to the northwest along with the Pacific plate, and they're gradually eroding away. And then look at this, a series of former islands now under sea mountains. They stretch hundreds of kilometers farther northwest. So the Hawaiian hotspot has been active for at least tens of millions of years. Well, in summary, I've focused on three types of plate boundaries, each of which is a region of dynamic surface geology. You have divergent boundaries. They feature ongoing volcanism and the formation of new crust. Convergent boundaries, they're the sites where old crust is swallowed up. Earthquakes and volcanoes follow the path of the subducting plate. And then transform boundaries, where two plates scrape by each other, and they're the site of some of our planet's most violent earthquakes. In the next lecture, I'll focus on the surface of the Earth and tell you about one of the Earth's great cycles, the water cycle.